Now let's consider two proportions, and we're interested in the difference between two independent proportions, P1 and P2. What do I mean by independent? It means they refer to different samples, to different groups of people or items. And in this example, as in the book, we've got P1 is 78 out of 252. This is combined data from a number of studies with novice participants in the telepathy experiments, and 78 out of 252, that's a proportion of 0.31, were correct. And we're comparing that proportion with P2, which is a much smaller sample of Juilliard students of artistic musical types, and 10 out of 20 of them happen to get correct responses, a proportion of 0.5. Now over here we have the familiar figure with the two independent proportions. Independent, of course, because they refer to totally different people. Independent proportions with their 95% confidence intervals, and as well because the effect size of interest to us is the difference between these two proportions. We plot that difference here on this difference axis. Of course, the confidence interval for this group, for P1, is quite short because we have 252 participants, whereas for this group with only 20, then we have a very long confidence interval, and these are independent. So as in chapter 7 with independent groups looking at means, this confidence interval on the difference is just a whisker longer than the longer of these two. It's just a whisker longer than the P2 confidence interval. And in fact, this difference we estimate to be around about 0.2, but with a very long confidence interval from about 0 to about 0.4. So because this group is quite small, we're not getting very good information at all about the difference between these proportions. And here we have it, the difference between the proportions, P2 minus P1 is 0.19, and the confidence interval on that difference is from about 0 to about 0.4. So we can conclude from this that we can't rule out the possibility that there's no difference between proportion correct in the underlying population. 0 here is within this confidence interval, so we have scarcely any evidence against 0 as a plausible value for the population difference. But the main message is we have a lot of uncertainty, a very long confidence interval here. Now, this is not the traditional way to analyse a 2x2 frequency table. So 78 and 10 and 174 and 10 are the four main observed frequencies, and 252 and 20, and also 88 and 184 are the marginal totals. This is a 2x2 table of frequencies reflecting two classifications. One classification is, left column here is the large number of novices, and right column here is the small group of Juilliard students. Then the other classification, the row classification, here is items correct and here is items incorrect. So for the Juilliard students we had 10 out of 20 were correct. And this chi-square analysis, and there's the symbol, the square of chi, the Greek letter, postulates that there's the null hypothesis of zero association between these two classification variables, the column variable and the row variable. And under the null hypothesis, you can calculate the expected frequencies in these four main cells, given that we've got 272 overall participants. The expected frequency in this cell, for example, is 81.5 something, here 6.47, and so on. Then chi-square is a measure of the discrepancy, the amount of departure between our observed frequencies and these expected frequencies expected under the null hypothesis. So the larger the chi-square, the more the divergence observed from expected, and the stronger the evidence we have that the null hypothesis is untenable. Now, applying the formula, chi-square here is 3.07. This has 1 degree of freedom in a 2x2 table. This is a slightly large value of chi-square under the null hypothesis. So there is a certain amount of departure of these observed frequencies from the expected. Looking up the distribution of the chi-square statistic, P is 0.08. So small, but not sufficiently small for us to reject the null hypothesis of no association between these two variables. You can read some of these pop-outs here, and they give you a little bit more explanation about what's going on. There's the value of chi-square. And traditionally, researchers would calculate chi-square and make their reject or not reject decision based on the p-value. So some red flags might be popping up in your mind when you hear that. There is an effect size measure for the degree of association in this 2x2 frequency table, and it's Greek phi, which is a measure of degree of association which can take values from 0 up to 1. And there's a little bit about it in this pop-out. And here we've got a value of phi of 0.11, which is very small, and so we've got a very small degree of association in this table. Going back to our analysis in terms of difference between two proportions, we can actually calculate the p-value for that difference using a null hypothesis of zero difference in the underlying populations, and we get 0.079, agreeing quite closely with the p-value for the chi-square analysis. Now, in fact, chi-square is an approximation. It really requires all expected frequencies to be greater than 5, and they are here, well, just 6.47. And this calculation based on proportions is generally a much better approximation. It can cope with even lower expected frequencies, so this is typically more accurate than that, although we're talking about minuscule sorts of differences. And anyway, if we follow our general approach of preferring estimation, we'll be doing very well here, because the accurate information about this difference is given by this point estimate of 0.2 and the confidence interval, which is very informative. It tells us that we basically have no support for the idea that we should reject 0 as a population difference, and any value from even a whisker below 0 up to around 0.4 is plausible for the true population difference. So that's a brief look at proportions, a single proportion and two proportions, difference between two independent proportions, and what ESCI offers for representing point estimates and interval estimates graphically. Proportions is really the one effect size we consider that you can apply to frequencies, and frequencies are just simple counts that you apply when your basic measure is a two-valued variable. For example, a test item is correct or incorrect, and so that's a variable with nominal or categorical scaling. So proportions can be extremely valuable. They can allow us to analyze and represent using estimation simple frequency data.